Hello everyone, I'm Zhendong from National University of Singapore, and this work is collaborative with my advisor Umang Mathur. So nowadays, concurrent programs are widely used. We could see have web servers, browsers, database systems, and operating systems. So writing reliable concurrent code and automated concurrency bug detection has been the subject of many researches for more than 5 decades. So as a result, a wide range of techniques do exist today. For example, we have static analysis and some model checking. But some disadvantages like false positives and low scalability limit their usability. So another technique is dynamic analysis. One looks at traces or executions of a running program and analyze them to declare the presence of or absence of bugs. So in this talk, I will focus on dynamic analysis. So formally, dynamic analysis problem is a membership problem. So we witness execution sigma, and also we have a bug language L which contains all buggy executions. And the question is asked whether this execution sigma belongs to this language L. So this technique is automated and often do not have false alarms and can scale to large software systems. But when it comes to concurrent programs, there is some problem. Why this is because concurrent programs are sensitive to thread scheduling, which means we might miss many bugs. So here is an example. We have two thread T1 and T2. Thread T1 will write to a buffer, and thread T2 will close the buffer. In naive dynamic analysis, we might notice an execution like this. So thread T1 first write to the buffer, then thread T2 close the buffer. Now, of course, it's okay, there's no problem. But can we just declare that there is no, the program is correct? Actually, we might. Okay, sorry. But there is a very similar possible execution like this. So thread T2 might first close the buffer, then thread T1 will write to the buffer. So we want to ask, if we just witness a good execution, can we predict the existence of a similar but buggy execution? So this motivates the idea of predictive monitoring. So in naive dynamic analysis, we ask this membership problem. And in predictive monitoring, we ask a problem is a bit different. So here we ask if we have an execution sigma, whether there exists a execution sigma prime, that sigma prime belongs to the language L. So we would like to use the power of prediction to enhance the coverage of dynamic analysis. So predictive monitoring has been used in many works to detect specific bugs, such as data race, deadlock, or atomicity checking. So in our work, we would like to understand the difficulty of predictive monitoring problem. However, so far our problem is not formal enough. The first thing we need to make clear is the notion of, the notion of similarity. So in concurrent program analysis, Mathur trace is often used to model executions. It provides a way to partition executions into equivalent classes. So Mathur traces start from defining independency between events in executions. So two neighboring independent events can be commuted without changing the behavior of the execution. So if you are in the keynote session earlier today, it is an example of using commutativity. So, So then the equivalence relation is obtained by swapping events consecutively. So here is a formal definition, but we can take a look at an example. So here we have an execution with two threads. So first, we know that event 5 and event 6 can be commuted. So then we got equivalent execution. Then furthermore, we can continue swapping event 3 and event 4. Then we have another one. Then later we can also swap event 4 and event 5. We have another equivalent execution. But here, can we swap event 2 and event 3? Actually, we cannot, because if we put read x before write x, it might read a different value, and it might change the control flow. So this is our notion of similarity. So in our work, we will ask predictive monitoring under Mathur trace. So let's take a look at the difficulty of the problem. So let's start from the naive dynamic analysis. So here, error can be any language. So it might be undecidable, but in many cases, error just a regular language, like in database dialog. So it means that it can be solved by a DFA. So it can be solved in linear time and constant space, and in a streaming way. It's very fast. So we also want our predictive monitoring can be solved in such efficient way. Why? Because in real-world programs, like web browsers, they generate millions of events in a very short span of time. But if the language error is regular, can we always have such an efficient algorithm for predictive monitoring? Unfortunately, the answer is no. So this is our first contribution. We provide a conditional lower bound for predictive monitoring against regular languages. So here we use fine-grained reduction. We assume that the strong exponential time hypothesis holds. Then we show that even for a very special subset of regular languages, stuff with regular language, the predictive monitoring cannot be solved faster than the order of the length of the execution to the power of alpha. Here, alpha is a constant related to the alphabet, and in concurrent programs, so the alpha is usually to be the number of threads. So, but in fact, in 1989, Bertoni, Maudi, and Sabadini proposed an algorithm to solve predictive monitoring against regular languages in this time and space complexity, which means our result is a matching lower bound, and the algorithm is very likely to be optimal. But we can observe that it is not suitable for dynamic analysis in practice. So in our work, we want to find a class of properties or languages whose predictive monitoring problem can be solved in constant space and also linear time and in the streaming way. And we also don't want to sacrifice its expressiveness, which means we want it to encode various useful program properties. So based on these requirements, we propose pattern languages. A pattern language contains all executions where some events occurred in the certain order. It is motivated by many real-world concurrency bugs, and there is a hypothesis called small depth hypothesis, which means that those bugs can be encoded in a very short pattern, meaning the D is very small. It's usually just 3 or 5. So here are some examples. For example, those examples are from Jefferson library. Here it says that we cannot concurrently iterate a collection and modify it. And the next one says that we cannot write to a buffer after close it. And our result says that predictive monitoring against pattern language can be solved in linear time and constant space, that's by automaton. So here we will briefly discuss our streaming algorithm to solve the predictive monitoring problem against pattern languages. So our streaming algorithm is based on 3 insights. So here first we consider a very easy case. If we are given the events, how can we check whether they can be reordered in the correct way? Here we can construct a very special partial order based on Mathur trace and check the partial order between pairs of events. The good thing is the partial order can be checked in constant space, and we only have d square pairs. So the whole checking can be just use constant space, and we have a DFA to solve the whole thing. And next, we'll ask how can we check for any D events? Okay, it is very easy because we just need to add non-determinism to this automata. So now we have an NFA, which non-deterministically chooses D events and do the same checking. But the problem is the space complexity is very large. So the last insight use a special monotonicity property such that we don't need to check every D event, and we reduce the space complexity to the order of D factorial times the size of alphabet. So remember that in most practical case, D is very small. It's just 3 or 5, and yeah. So actually, this space complexity is very small. Remember that the major component of our algorithm to check the partial order. And we also have a vector clock-based algorithm. We use this very classical vector clock, and the vector clock of an event it maintains the number of events in each thread that the event E knows about. And to check the partial order between two events, we just need to compare the two vector clocks. And our vector clock-based implementation uses space which is linear to the number of threads. So the last part is evaluation. We implement our algorithm in Rapid, which is a framework of dynamic analysis on concurrent programs. So we encode some Java standard library properties in Python languages and test them on some open source programs. And here is an example. So here we have a class and with two methods. One method will iterate the set subtitles, and the other one will add something to this set. So our algorithm can predict the violation of the property from a good execution to a bad one. So here we will see that the modification will interleaves between two iterations. Our evaluation also shows the scalability. We compare our algorithm with the traditional algorithm proposed by Bertoni. We can see that our algorithm works well even when the execution is very large. However, the traditional algorithm uses up spaces very quickly. Then, to wrap up, in our work, we focus on predictive monitoring under Mathur traces. And for this question, we construct a conditional lower bound against the regular languages. This is a matching lower bound. And since we want predictive monitoring algorithm suitable for real-world programs, we propose Python languages which capture executions where some events occur in a certain order. And then we design the algorithm to solve its predictive monitoring problems and in constant space, near time, and in a streaming way. Finally, our evaluation shows its ability to find practical bugs and its scalability. Well, thank you.
Thank you. Questions? So I'll start with a naive question. In those pattern languages, are there any constraints on the sigma? For example, you said if I open a file, I write, I close, I write again. Well, and there were sigmas in between. How do I know that in that sigma in between I didn't open it again?
Yes.
And then it would make it valid.
Yes, that one is a case that we cannot encode it in Python languages. And we're also thinking of more generalized Python languages. So in the middle, we don't have sigma, but some sigma 1, sigma 2. So we can just, then for those languages, we can encode this file open, file close. But for that one, we don't have a very efficient algorithm.
So you mean that if I had a trace where if I had a pattern that said I'm not allowed to write after I closed, and I had a trace where I closed, I opened, I wrote, then this would fail the check.
Yeah, because you have the close and the write, so you don't care about what is in the middle.
All right. Other questions, comments?
If instead of this kind of linear A1 through AD, I wanted to kind of model a DAG. Let's say I want to say A1 followed by A2 or A3 and then followed by A4. Would things differ greatly?
Yeah, I think there is some efficient algorithm to solve this. If it is not linear but a DAG.
So then maybe can we generalize that to low DAG width graphs? Or
Sorry?
can we go more wild from DAGs and go to low DAG width graphs?
Yeah, I think then we might need some width in the complexity. Then I think a very similar algorithm should also work. But yeah. I need to think it.
I guess it's worth thinking about it because that would be a great generalization of the pattern you currently have up there. Yeah.
Okay, thank you.
Thanks.
Hi, thank you for the talk. How do you handle critical sections? Like if someone acquires a mutex and does iter next, iter add, how will it be reflected in the model?
In the model, then we cannot swap any critical sections. And this is also a weakness of our model. And so in the future work, we are trying to relax this part and to get a better model.
Hello. Is it possible to have properties like LTL within this model? LTL properties, can it be done?
So LTL is just equivalent to star-free language, regular language. So I think it's also fit in the matching lower bound.
In constant space streaming?
I think we cannot do. Oh, you mean constant space?
Constant space streaming algorithm might be.
But we cannot do it in linear time, because our this conditional lower bound says that it's very likely that we cannot have a faster algorithm than this polynomial one.
So one last question, and in the meantime, I would like to ask Dominic to set up, at least to connect his laptop, not take the microphone yet. Is there any last question? I'm sorry, I have got one more. Those A's that are events like open, close, and so on, can they have some arguments, and can you express properties of those arguments? Can I say that if I push something and I pop it, then it should be the same?
I think that should rely on the log, meaning if you have a very good instrumentation tool. But I think the problem is you might have some infinite possible arguments. Yeah. I think I need to think about it later. Okay, thank you.
Okay, let's thank Zhendong.